Good afternoon, my YouTube viewers. In this video, we're going to be talking about some experimental design, and the specific experimental design that we're going to be covering is crossover design. So crossover design is used in studies where the same subjects receive multiple treatments in a randomized sequence, such as drug trials, to account for individual variability. And then we've got a practice question that we're going to go over in this video. A pharmaceutical company is testing two different pain relief medications. Each participant receives both drugs in random order with a washout period in between to avoid carryover effects. How can this experiment be designed, and what are the advantages of using a crossover design in this scenario? So in order to answer this question, what we're going to do is we're going to write a program in Python. And so in order to write the program in Python, what we're going to have to do is we're going to have to import some libraries that are going to be needed to actually execute the program. So we're going to import NumPy as NP, which is the numeric library that also creates NumPy arrays. We're going to import Pandas as PD, which is a data processing library, which also creates data frames and series. We're going to import matplotlib.pyplot as PLT, which is a visualization library. And from scipy.stats, we're going to import ttest_rel. So scipy is Python's scientific library, and stats is a statistical module within scipy. In ttest_rel, it means it's a t-test, but it's a t-test that's performed when the samples are related to each other. If the samples are not related to each other, then it's going to be a ttest_ind. But because the samples are related to each other, we're going to be using ttest_rel. And you always have to make sure that you're using the correct t-test when performing a hypothesis test, because if the samples are related to each other and you use the t-test for the individual, then it's not going to come out with the correct values or the values that it should be. So that's why you should use ttest_rel in this particular one, because the samples are related to each other. So after we have imported the libraries, then what we're going to do is we're going to simulate data for a crossover experiment. And the first thing we're going to do in that regard is to set our seed. And the reason why we set our seed is so we can make sure that whenever we run the program, all the variables are initialized to the same data. So that's why we set our seed. And you set your seed by typing np.random.seed, and you can type any number that you want within the brackets. And now we're going to define the variable n participants equals 30. So that means you've got 30 participants. So we're going to generate pain reduction scores for drug A and drug B. And group 1 receives drug A first, then drug B. And group 2 receives drug B first, and then drug A. So drug A first equals np.random.normal brackets 50, 10, n participants floor 2. So that means it's going to be a normal distribution with a mean of 50, a standard deviation of 10, and a sample size of 15. And drug B second equals np.random.normal brackets 55, 10, n participants floor 2. So that's a mean of 55, standard deviation of 10, and sample size of 15. And then group 2 is going to be receives drug B first, then drug A. So group 2 is drug B first equals np.random.normal brackets 55, 10, comma, in participants floor 2. So that means the median is 50 and the standard deviation is 10 and the number of participants is 15. And drug A second equals np.random.normal brackets 50, 10, in participants floor 2. So that means a mean of 50, a standard deviation of 10, and number of participants as 15. So now we're going to create a data frame to combine the data using pandas. Data equals PD data frame brackets. Participant equals np.arrange brackets 1, in participants plus 1. So that's going to be the participant number. And drug A is np concatenate brackets drug A first, drug A second. And drug B equals np concatenate brackets drug B first, drug B second. And then the sequence is A to B times in participants floor 2 plus B to A times in participants floor 2. So the in participants floor 2 is 15 each. So there's going to be a sequence of 15 from A to B, and then another sequence of 15 from B to A. So now we're going to calculate the mean scores for each drug. Mean A equals data drug A dot mean brackets. Mean B equals data drug B dot mean brackets. So now we're going to perform the paired t-test. So t-stat, p-value equals t-test underscore rel brackets data drug A, data drug B. Then we're going to print the results, and we're going to print crossover experiment results, mean pain reduction drug A, mean pain reduction drug B, then the t statistic, and then the p-value. And your p-value is your probability, and so it's going to be a percentage. So crossover experiment, mean pain reduction drug A is 50.2 and mean pain reduction drug B is 51.7. So your t statistic is -698 and your p-value is 0.491, and the p-value is greater than 0.05, so that means the null hypothesis will have to be accepted. And the null hypothesis is no statistically significant difference between drug A and drug B. So drug B, is just slightly, just like maybe 1.5 points greater than drug A. So if the doctors would want to choose a drug, then drug B would just be slightly better than drug A. So now we check about our p-value. If p-value is less than 0.05, you print there is a statistically significant difference between drug A and drug B, but it wasn't great. It wasn't less than 0.05. It was greater than 0.05. So you print result, no statistically significant difference between drug A and drug B. But having said that, drug B scored like maybe 1.5 more better than 1A. So let's see what it says. It says mean pain reduction. So it scored just a very small amount better than drug A. So drug B would be the one that I would go for. But, obviously this is just a test to see which one is the best. So now we're going to visualize the bar plot of mean pain reduction, PLT dot figure brackets big size equals 6, 4, Labels is a list of drug A, drug B. Means is a list of mean A, mean B. Standard deviations equals data is a list of data drug A.std, data.drug B.std. And then now we create our bar chart, plt.bar brackets labels, means, YERR equals STD underscore DEVS, that's your standard deviation, cap size equals 10, color equals blue and orange, and alpha equals 75. And then now we're going to customize the plot. So the title of the plot is Crossover Study Pain Reduction for Drug A versus Drug B. Y label is mean pain reduction. X label is drug. And the grid is axis equals Y, line style equals double dash, and alpha equals 0.7. And then also, in addition to that, we're just going to put a piece of code in the to be able to put the numbers of the means on top of the bars. And then it's a tight layout, and we're going to show the chart, and this is what the graph looks like. And so if I was going to select a pain medication because drug B was slightly better than drug A, I would check drug B. But then you also have to take a lot of other details into consideration too, because the different drugs have different side effects, so you have to take the side effects into consideration, and the different drugs interact with other drugs that the patient might be taking, and so you have to take that into consideration. So there are a lot of things that need to be taken into consideration when selecting a drug. So that concludes this video. In the next video, I will be talking about some more experimental design topics. So I hope that you decide to watch it.